So continuing on with our exploration of logs, we're going to take a look at some graphs today. And we are going to see how they relate to their inverse functions. So some of our exponential functions that we've been previously studying. So for this first one, we're going to consider the log function y equals log base 3 of x and its inverse, which would be the exponential function y equals 3 to the x. And we're going to construct a table of values for these that then we're going to use to plot on the side. So using our exponential function, 3 to the x, if I have 3 to the negative 2, so I have to think it's going to be a 1 over answer, and it would be 1 over 3 squared, which would be 9. 3 to the negative 1, again, I'd have a 1 over 3 to the first power, or 3. So now I have anything raised to the 0 we know is 1. 3 to the first power is 3, and 3 squared is 9. So if we go to plot these out, I'm going to start with going over 0 up 1, then I'm going to go over 1 up 3, and then over 2 up 9. Let's not forget about our fractional values. Do your best. So we have over negative 1 up a third, and over negative 2 up a ninth. And again, with our exponential functions, we know that they're going to be asymptotic to the x-axis. So don't forget to label your graph. That shouldn't be curling up, that's going to be the flat. Okay. Now, knowing that these are inverse operations, that should make this table not too bad. We just think flip your x and y. So if my x value is negative 2 for my exponential function, that means my y value is negative 2. If my y value that corresponds with that was 1/9, that means your x value is 1/9. So we're just flipping these around because they are inverse operations. We have 3 and a 1, and we have a 9 and a 2. Okay. So graphing these, again, if we have our fractional values, we just have to be really careful. 1/9 down 2, 1/3 down 1. Going over a value of 1, down 0, over a value of 3, and we're going to go up 1, over a value of 9, and we're going to go up 2. So now we get a graph that's like this. And our, don't forget our label. Okay. So we have filled out those charts, we have graphed our equations, and now we want to take a look at the domain and the range of these. So remember, domain is going with your x values, and the range is going with your y values. So your domain for our exponential function 3 to the x, we have all x values. Okay, I can use all x values left and right, no problem. So our domain, we can say here, would be negative infinity to positive infinity. And remember, soft brackets or parentheses because we can't include those numbers. Now your range for this function is all of your y values. And keep in mind, it's not touching this x-axis here. It gets super close, but it doesn't touch it. So I can't include 0, but I still want to mention 0. And it's going to go all the way up to infinity without stop. So I don't want to include 0. That's where that soft bracket comes into place. And it goes out to infinity. Now, we've looked at this before, and just like we set up above when we made the chart, flip your x and y. So flip your domain and range for our inverse operations. That means the domain of the log function should be the range of our exponential function, and the range of our log function should be the domain of our exponential. So if we go up and just check, just to make sure. So we just said the domain should be going from 0, but not including 0, which that looks good, all the way out to infinity, which that looks good. And our range, it says, goes negative infinity to positive infinity. Okay, and this is growing. This keeps going down, 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 and keeps going up. It's just a slow increase up. So those look good. Okay, our next one we're going to graph. And we're going to use our calculator to do this. We are going to graph the function log base 10 of x. Remember, that's our common log. And it says we want to label the x-intercept, and then again, we're going to state our domain and range. So if we go to our calculator, we're going to get our log function, our common log being 10. Now you can either type in the 10 to make sure that that's in there, or you can leave it blank because it is the common log, and it will graph it just the same. So there's our log function. And again, it looks like it stops. It does not stop. It gets super duper close. And if you go to your table to analyze it, as you get closer to 0, now what your table is going to do is it's going to tell you it's undefined at 0. If we were to change this in our menu and we were to, go to our table settings, and we could edit the table settings, which is number 5. And so I'm going to just change the table. It says table step. I can change this to a different value. So instead of having it go by integer values, I'm going to change it just to be 0.01. And I'm going to say OK. And there wasn't a domain error. The table just didn't want to work today. But you can see if I were to look at this chart, it's getting super close. It's getting smaller and smaller and smaller. As the x value is getting closer and closer to 0, I can see my number is decreasing, decreasing, decreasing. And as I change that, I can make that bigger. And I could see it's going to get closer and closer to 0, but never actually touch 0. Okay? So with that being said, we wanted to find the x-intercept of our graph, and then we were going to state this for the domain and range. So if I go back to just looking at the graph, I can see the x-intercept is at 1. So it gets super close to our axis here. My x-intercept I know is going to be at the location 1. It's continually increasing, slow little increase, but we have something that looks like that. So our domain and range, the domain, again, like we were looking at that table, it's not getting lower than 0, but it's going to go all the way out to infinity. And I want that soft bracket because we saw values at like 0.01 and 0.02 and 0.03. So I need things that are super close to 0, just not 0. And the range, again, I can see this is going all the way down and all the way up to infinity. So this next one, we're going to try and pick a graph from an equation listed. So this is taking a look now at transformations. And I want to think to myself, how is this going to change our graph? So looking at what we have, it looks like I'm changing the x value by either adding or subtracting. So when I add or subtract to the x value, anything in here, that's shifting it either left or right. Okay. If it is going to go to the left, this is almost backwards from what we would think. If it's going to go to the left, I should see a plus. If it's going to go to the right, I should see a minus. Okay, and the numbers added down here, this is telling me it's going to shift it either up or down. Now this is a normal notation, so if it's up, again, I want to think plus. If it's down, I want to think minus. So knowing before we had an x-intercept that was located here at that location 1, 0, I'm noticing that now my x-intercept is back here. It looks like it's been shifted back or to the left by a value of 2. So if I'm thinking up here, shift left, I want a plus 2. Okay, and I want to take a look at maybe where that's going to be located. But now I also have to take into consideration either it's going up or it's going down 1. So how would I figure that out? Well, if I took a look at, maybe let's plug in a value, and I took a test point. Let's say that test point was 1, 1. Okay, so if I plugged in the value 1, 1, and let me plug it into our choice number 3. Let's just try this for instance. So if I took a look at the point 1, 1, And I'm doing that because I'm noticing that point is on the graph. And I want to see what is that going to satisfy? Which equation is that going to satisfy? Okay, so which equation? Well, if I tried to plug it, let's say, into this one. So wherever I see an x, I make it a 1. Wherever I see a y, I make it a 1. And I want to see, are those going to be equal? So this is saying 4, right, if I simplify this. So log base 2 of 4 minus 1. Okay, so log base 2 of 4, you could either use your calculator or you could plug it in. You could do what we did our last class, which is trying to simplify that down. That would get you a value of 2 minus 1. And does 2 minus 1 equal 1? It sure does. So that's going to show you that that is our function. Now you may be saying, well, why isn't it a back 2? Why didn't it go into this equation? Well, keep in mind we have this up or down motion that we are also changing here. So this is actually saying the graph had to shift, I could say, to the left 3, and it had to go down 1. So now let's check that out. If I shifted that left 3 and down 1, notice what we would have here. That would be your x-intercept that has shifted from this location. So it went actually back 3 and down 1. So when you find your graph, 1, you can plug this in your calculator and just kind of guess and check your way. 2, it's always a good idea to plug a value in and try and evaluate it and see would that actually work. Okay, and take a point that's on the graph and plug it in. Okay, let's try another one. So we're going to determine the domain of the function, and we're going to state our answer in set builder notation. So I'm going to go and graph this out so we have a picture of this. So we have the function log base 2. Type in our 2, arrow over, and now we have 3x minus 4. And so here's our graph. And we have to determine the domain of this function. We're going to state our answer in set builder notation. So something that I'm hoping that we're noticing is these graphs, and like we have back on this page up here, the fact that finding the log of a non-positive number, meaning negative or 0, is not possible in the real number system. It allows us to find the domains of a variety of log functions. So non-negatives or zeros, it's not happening. Remember that 0, it's not touching that axis, that y-axis, and they haven't been in the negative location. So with that being said, if I were to take a look at 3x minus 4, I know that this cannot be negative or it can't be 0. So that means it has to be greater than 0, which looking at the graph, I can see it's greater than 0. What I need to do is figure out how close is this graph? What is this getting to? What is that value that it's trying to approach? So if I were to solve this, I could add over the 4 and divide by 3, and that would get me the value, x being greater than 4/3. So if we were to write this in set builder notation is our squiggle brackets, and I would say here x such that x is greater than 4/3. If we did it in just our other kind of bracketed notation, different way you could say this is, again, I can't include 4/3, so I get that soft bracket, and then I know it can go all the way out to infinity. So let's go back to our graph. And this line that this graph is asymptotic to would be the equation x equals 4/3. Notice that's greater, slightly greater than 1. So it's a little bit bigger than 1. It won't approach it, but notice all of those other positive values will work in this function. Okay, and then we have our last question here. So all logs with bases larger than 1 are always increasing. This increasing nature can be seen by calculating their average rate of change. Remember, that's kind of like slope for a line. So we're going to consider our common log, and we're going to set up and evaluate an expression for the average rate of change over the interval from 1 to 10. So these are my x values. I would need to figure out the y values that would go with it. So it would be like saying log of 10, that's my y value, minus log of 1. And then I would divide that by my x's. Okay. Keep in mind, if we were to write these as coordinates, I would have the coordinate 1 comma log of 1, and I would have the coordinate 10 comma log of 10. Now, maybe you don't know what the log of 1 and the log of 10 is. That's okay. We have a calculator. Grab your calculator, get yourself a calculator page, and we can evaluate it. So I want to figure out the log of 1. Now, notice I'm leaving that base 10 blank. That's okay, because it's a log base 10. So the log of 1 is 0. And if I do this again, I want to figure out the log of 10. And the log of 10 is 1. Now, we could do this with exponential functions. We could do this with the calculator. And so now we have our values, and I have 1 minus 0, and 10 minus 1 is 9. So I get the value 1 over 9. That's our average rate of change. Now they're asking us to do the same thing, but for different values, for the range of 1 to 100. So again, if I were thinking coordinates, it would be 1 comma log of 1, and it would be 100 comma log of 100. Okay, so we need to evaluate log of 100. We know what log of 1 is. So if I type that into our calculator, log of 100, we get the answer 2. And again, we could do this with exponential functions. So I would have log of 100 minus log of 1. So 2 minus 0 over 100 minus 1. And if we simplify, we get 2 over 99. So notice different rate of change, which should make sense because it's not a line. And it says, what do these two answers tell you about the changing slope of the function? The function slope is getting smaller. Okay, so I could say the slope gets smaller as our x is getting larger. So that should make sense. The slope, all right, if I'm looking at the rate of change of this first section, changes super fast. If I look at the rate of change over here, it's still getting faster. If I look at the rate of change going, like, say, from here to here, it's going to slow down. And if I look even at other intervals, I'm going to see it's going to slow down. It's going to start to taper off. It's still going to change, but it's going to be a much slower slope or rate of change. Okay, bring your questions to class tomorrow, and we will answer them. Hope you guys have a great day.